Howdy again. Thank you, much better. So before we start the class, and we have a survey, Jesse sent that out to everybody. So what's the topic you want? One of the items we got is a comprehensive coverage of radiative transfer. Comprehensive for even we spent all 5 days on this, and we couldn't be comprehensive. So we decided that, okay, we cannot do comprehensive, but how about we do just a short, brief overview. The other extreme of comprehensive. Basically, it's a half semester of lecture classwork compressed into 1 hour. So I don't know how well it will go, but I will try to be focused on the physics concept, just give you a qualitative understanding of the physics process. And then I will leave the quantitative work to those who really need it. Really, in your PhD study, you really need that. You probably want to spend much more time in this various topic that I'm going to cover, right? So that's my motivation part. First is why can you see the world? Simply because there are 3 elements in the remote sensing world. Light source, right? Emit light, hit a target, and get into your eyes. That's the reason that you can see. The media is electromagnetic waves, right? So in remote sensing, there is always 3 basic elements: source, target, and sensor. Your eyes, it's a very good sensor to help you navigate this world, right? 3 elements. So the key thing here is the medium that we rely on to see the world. It's electromagnetic waves. I'm showing you a very simple example here. It's a plane wave. Plane wave is the basic elementary wave we use to do many analysis of this world. We have a mathematical tool called Fourier transform. You can decompose any arbitrary electromagnetic wave into monochromatic electromagnetic waves, which we call Fourier analysis. This is a basic structure of the wave. You have a wavelength, which is a vector, by the way, right? Electromagnetic wave, it's a vector wave. It actually have a direction. This is the oscillation part. So physically speaking, this complex wave, we only take the real part of it, namely cosine kz minus omega z, right? So only the real part matters, but the complex wave is introduced to help us do the mathematical manipulation much easier. And talking about this part here, this omega bar here, which is 2 pi over t. It's a period of the wave. That gives us the frequency information. Of course, 1 over t, it's the frequency we define. The spectral range from very short gamma ray all the way to radio waves, right? So the scale, what the pace is mainly focusing about, it's near this very small range from ultraviolet to visible to very small section of the up to shortwave infrared, which is 2 micron. 2 micron is the longest wavelength that PACE will cover. But basically, the wavelength of EM wave, we have this unified view. It can be as short as the smallest dimension we can detect in this universe to as long as the universe. That's a basic view of electromagnetic wave today. That's a spectrum that lambda with its wavelength, which is related to frequency and the speed in this way. So you can see different wavelengths corresponding to different size of the objects that we see. Right? This is my my favorite slides, so that you always look at it and get a grasp of the how large range of the EM wave is. Then that's the oscillation part, the period part, and once we get into the polarization nature of EM waves, it does have directions. So for example, I have a laser pointer, I shoot in this direction, you see the red dot there, right? So there is a wave front propagating from here to there. The laser is very unidirectional, but it still have a divergence angle. So perpendicular to the direction of propagation, if you have a cross section, that you see the wave front. The wave front, there is an electromagnetic vector on the wave front. It's polarized, pointing into different directions. So that's why the nature of EM waves is polarized, so we can use that information to get what we're trying to see, right? Our eyes, some people can see very faint pictures of polarized light, but most of us, we can't see, right? Our eyes only see the total intensity of the EM waves. So we have polarimeters to help us to decompose the information. To mathematically describe it, we introduce a plane of reference. Later on, I have a slides on that. Basically, that light going this way, and we have a plane contain this line, and we decomposed our electromagnetic vector into two components. This is perpendicular, this is parallel. You can decompose the vector into two arbitrary perpendicular directions, right? It's a vector decomposition. So this is why we have these two directions. And once you have that two decomposition, we introduce these four elements, which is mathematical combination of E perpendicular and E parallel, which we call IQUV. It's the Stokes parameters. The Stokes parameters help us to analyze polarized light better because its quantities based on intensity, not amplitudes. Amplitudes, I don't know how well we can measure that. It's very hard to measure, but intensities, we can measure pretty well. Then by measuring these different components, we understand light, the whole nature of polarized light to a new degree. This I, which is total intensity, it's similar to what our eyes can see. And these Q and U are parameters we use to describe polarized light, linearly polarized light, right? And this V, it's a circular polarization, which is, in that case, you have a E vector rotating either this way or this way. It's circularly polarized light. But in general, we only see elliptically polarized light. In that case, the E vectors in the two directions, they do not have equal amplitudes. So with these Stokes parameters, we can use to describe the state of the polarization state of a light. For an arbitrary light you come in, we can use these four parameters to describe the state, right? That's the basic parameters we use. like the pace parameters will provide you I, Q, and U, but not V. V is very weak in the atmosphere, so we just throw it away, or we didn't even measure that parameter for the sake of data volume compression. Light scattering. This describes how an object interacts with a particle. So you have a incident light. Again, it's decomposed into two different directions, right? And it hits a scattering particle. It's scattered into a different direction. So the plane, which contains both the incident light and the scatter light, you have two directions. Think my arm, one pointing this way, one pointing this way. My two arms form a plane, right? That's what we call scattering plane. The scattering plane, we use that as a reference plane. We decompose the electromagnetic vector into two directions. One is perpendicular, one is parallel. And mathematically, we can relate these vectors and these vectors. And that's the scattering plane we just defined. And we call the relation of this E parallel and E perpendicular, E parallel and E perpendicular. This S means scattered light, scattered wave. This I means incident. And this 2 by 2 matrix we call amplitude scattering matrix. And even though it's 2 by 2, but all four numbers are complex. So we have more information than what you see. By doing, again, we can't measure the amplitude that well. We just don't have a good sensor for the amplitudes. But we do have good sensors for intensities. So that's why we introduced this Stokes parameter. And correspondingly, you will have matrix to connect these incident light Stokes parameters to the scattered light Stokes parameters. And instead of 2 by 2, now you have 4 by 4. The catch is that here, the 4 by 4 matrix are all real numbers. These are all real numbers. So if you give me an amplitude scattering matrix, will contain the same information as this Miller matrix we call Miller matrix. And these Miller matrix elements are connected to the amplitude scattering matrix. So don't be, so I know some of you have prior knowledge on this. So bear with me, I'm trying to explain. But if you have not get exposed to this knowledge yet, so just to see mathematically they are connect to each other in a way. I only showed these 4 elements, but for all other elements can be expressed in terms of S1 and S2, S4 and S3. So the 4 2 by 2 complex matrices. And most used is this one, the M11, the first one. We normalized in terms of the scattering matrix, scattering cross-section. This element here, C scat, it's called scattering cross-section. It describes the total, it describes how well a particle scattered light. Its unit is in meter squared. It's a unit of area. Namely, if you have a flashlight, you put a thing to block the light, you see a projection, right? You see an area. The larger your block or your object, you have a larger shadow, right? The bigger the shadow, you see the better a scattered light. in a way. So that's the intuitively how do we understand this fellow here. It's a quantity in the unit of area which describe how efficient it can scatter light, right? And this M11, it's a function of a scattering angle. It's a function of scattering angle. But this one, it's integrated value, so it's integrate all the scattering angles so that you remove that dependence. By dividing this and you multiply 4 pi, it's just convention. You get what we call phase function. Phase function tells you how the light, scattered light, distribute over the solid angle, 4 pi solid angle. So if you have a light coming to this way, I block it, blocked it, you don't see it. But if I have much, much smaller particles, you will still see it over there. But you have scattered light all over the 4 pi space, solid angle space. And two other quantities, this is called absorption cross-section, which tells us how strong the particle absorb light. And the total of them, summation of them, is called the extinction cross-section. So absorption plus scattering equal to extinction. These three are not independent to each other. Only two are independent. So don't think this is trivial, because once you get it, you will have to know you only have to pick two. Recently we tried to develop a ocean color remote sensing algorithm that we actually have the dilemma to decide whether we pick the extinction as the free parameter, or extinction and absorption, or we determine it's absorption and scattering. It's ideally it doesn't matter, but in reality there is consequences of that selection. So light scattered by mediums, for example, in atmosphere and ocean. In atmosphere we have molecules, aerosols, clouds. Lauren this morning have covered that part, right? So for Rayleigh scattering, it's a name we gave to light scattering by molecules. The molecules, the phase function is proportional to this 1 plus cosine theta squared. Theta is the scattering angle. Basically, it's a symmetrical looking. The vector length of this vector tell you how strong it's scattering in that direction. So light source coming here is scattered equally for the forward scattering and the backward scattering. Equally. And in the middle is kind of a minimum. And I think most importantly, you folks need to know this. The scattered light from molecules, or in the atmosphere, there are so much molecules. The scattered light is proportional to, or inversely proportional to lambda power of 4. So the shorter the wavelength, the stronger it gets scattered, right? This is a very elegant result that back in the old days, amazing scientists just get this argument by dimension analysis. They don't need to even use much complex mathematics. They just use a dimension analysis, they can get this result. Very, very intuitive, but very, very powerful result. This explains why the sky is blue, because blue light, the wavelength is shorter, so the scattering cross-section is larger, increase proportional to this factor. So the sunlight coming, it's scattered much, much strongly by the molecules, right? For aerosol and clouds, this factor will be much, much smaller, right? Depending on the size of the scatter, depending on the size, okay? Let me pause here. Any questions so far? I hope I don't overwhelm you. As I'm talking, I realize how long this talk will be. I don't even have confidence that I can finish in time. But yeah, I'm barely scratching the surface right now. Okay. We know the Mueller matrix is the 4x4 matrix to describe the scattering behavior of a particle. So in general, we need 4x4 matrix. So for scattering by molecules, this is how does it look, 4x4. Note that this is 0, 0, 0, 0, 0. So you only have 1, 2, 3, 4, 5, 6 non-zero elements. You only have 6. This is the same result as spherical particles. You only have 6. So this is a plot of this A1. A1 is this one. And it's equally from this one and this one, the middle, 90 degree. So light comes up, scattering to that direction. That's 90 degree of scattering angle. So for Rayleigh scattering, you have minimum at 90 degree and a maximum at this and this. And here I did not show in the previous slides, this row here is to account for the fact that the molecules are not what we call depolarization factor. So we use this to describe all the different non-sphericity of the molecules. They have structures at different dimensions. So we use that factor to account for the difference. For air, the average rho is 0.028, the value. Okay, light scattering by spherical particles, because molecules are really, really small. For aerosol and clouds, we use a better model than the Rayleigh scattering. So the better model, one of the primary model we use is called Mean scattering. Mean scattering is a light scattering by spherical particles. No matter how big your particle is, as long as it's spherical, we call that Lorentz mean scattering. Basically, I'm not going to read through these bulletins because you can read. Basically, it's that a EM wave comes in, you hit the particle, and being scattered, right? We can solve this in the frequency domain. Namely, we only solve it in a single frequency, assuming the light is a monochromatic plane wave, and you try to solve the Maxwell equations in the frequency domain, which we call Helmholtz equation, which we show here. If you see the cursor, it's right here. That's the equation we see. So in the frequency domain, light scattering by an arbitrary particle can be solved by solving these equations. The difference is the boundary condition. So you have a spherical interface here. The spherical interface is easier to be solved if we use a functional base called vector harmonicas, vector spherical harmonicas. There are a set of mathematical equations which are built for spherical waves. That if we use that spherical waves, make it easier for us to solve this particular question, particular particle, right? And basically, you in the frequency domain, you have monochromatic waves, and you impose the boundary condition on the surface, and you solve the unknowns and get the scattering characterization. That's a basic physics idea. And you can see for very small particles, this is consistent with the mean theory, by the way, the Rayleigh scattering. The forward and the back, they are equally amplitude in the middle, it's kind of small. If the particle size gets larger, you have larger forward scattering and smaller backward scattering, right? And even larger particle, you have this even more very, very prolonged, very huge, large forward scattering peak by larger particles. Even though these slides separate mean scattering and the larger particles, but this is terminology. We can have a philosophical debates on the use of mean theory, but strictly speaking, mean theory applies to any size particle as long as it's spherical, right? And theoretically speaking, the mean scattering only depends on this thing, which is 2 pi times radius over lambda, we call size parameter, and the refractive index, n. N is a complex number, including real and imaginary, right? So these 2 parameters determine the whole scattering pattern of everything. If you have a larger particle versus a longer wavelength, and another situation, you have a smaller particle and a shorter wavelength, as long as the ratio are the same and the refractive index are same, you get the same scattering pattern, right? So again, Lauren covered this morning, talking about infrared and visible. You have different size particle, different wavelengths, so you have the sensitivity of different particles. And again, here it's a plot of scattering efficiency. Scattering efficiency is another quantity that we introduced to do. Basically, it's the scattering cross-section over the area of the spherical particle. It's a ratio. Namely, we have this intuitive way of looking at things, how big they are from the projected area. So this scattering cross-section, the ratio of the scattering cross-section to the projected shadow of a particle give us we call efficiency. It's another term we use to describe light scattering. So by looking at this, you can see this x-axis is a size parameter. Increase as this efficiency increase as this size parameter increase. And once it goes to a peak, this peak is around some 2 to 3. And it goes into these oscillatory behaviors. And it do go into 2 branches. One is absorptive, one is non-absorptive. One is absorptive, it goes to 1. Namely, your scattering efficiency, it's when the particle size is very large, you get the same efficiency as your shadow, as your own geometric area. But if it's non-absorptive, it actually goes to 2. That's why you see the cloud remote sensing, and the remote sensing is kind of people very trying to be as efficient as they are. They don't want to use, even mean calculation is very efficient. They don't want to use that at all. They just put a 2 there for this efficiency. That's the reason, because ultimately for the cloud particles, which is very large compared to the wavelength you're considering, so they just put a 2 there, being whatever name you call it, lazy or or being efficient. So yeah, that's the difference. Available me codes. So I don't want to teach you how to write a me code, which is well developed. So you can have the references here. I think the most well written is the Vscope, and it's not. So when I started to use me code, his code is still available online. And eventually, the website is not accessible anymore. So luckily, I think somebody else put it, this guy, put Wiscombe's Miko there. So grab it while you can, while you're still there. I think it's the standard of the standard of Miko that everybody should look into. If you do scattering, you should look into his code and see how he write it. The caveat of this code is that in air, the particle is not monosize. It's you have particles with all different size, right? So you kind of want to have an integration of different size distribution. This code only calculate a single size spherical particle. If you want to do a size distribution, you are on your own, right? You need to know how to do the size distribution integration yourself. Another one is by Mishinko. I put his book here, the link, and his code. Again, I don't know how long, probably Brian will know better how long this code will be there in the website.
For a pretty long time. We're in the process of moving it though, so that it's in a different part of the site that would just be the tools. So it's not just under Michael's name.
Okay, so you are putting into a more permanent repository. Yeah, so Michael passed away. So he's the one of the, I wouldn't say one, but he is in the light scattering community, he is highly respected. He did so many work. And unfortunately, he passed away. So I was trying to say, download this code while it's still there, but probably it's going to be there for a long time. And this third line put there, there is many other tools you can go there. I don't mean this to be a complete list of things that you can use, but it's just several that I know which works, right? Any questions on the me code part? Me scattering? I think I'm lost in you folks. Well, the slides is there. You can download it and send me emails if you have questions on these things.
How long do you need a short video?
Well, yeah. Go ahead.
I'm a little lost on the difference between scattering versus shadow. So like I'm envisioning a light beam coming in and hitting a particle. If there's a shadow, then you wouldn't get anything passing through on the opposite side of the light beam, right? But then the scattering diagrams, there's the most strong arrow on the exact opposite side of the light beam.
Yeah, to explain that, we have to remind ourselves light is a wave. It's not a particle. If you have a particle, you can either block it or let it go, right? But a wave, once you have, think about this way, you have a wave and the particle size is comparable to the wave or even smaller. And then when you have that, you kind of excite secondary waves around that. The secondary wave will propagate in all different directions. And the distribution is determined by the geo distribution of the secondary waves. So waves is the key word to understand how it's different from our experience. In our experience, you have a shadow. That's the geometric nature of light. One wavelength is much shorter than the object it's getting into interaction. But if the particle size is much smaller comparable to the wavelength, you really need to use the wave type of thinking on that. Does that explain?
Yes, thank you.
Okay. Anything else? Okay. I talked about light scattering by molecules, and I covered the light scattering by spherical particles. But in general, our world is not perfect. And I'm certainly not a spherical shape, right? I'm have my head, my body. So if you want to solve light scattering by me, how do you do it, right? For example, if you have a meter wavelength wave scattered on me, for example, probably a microwave or even longer radio wave scattered by me, how do you solve that, right? We need some general method. One of the method is called FDTD. It's called finite difference time domain. Finite difference time domain method. This method is just to solve the Maxwell equations in the most native way, in the time domain. Namely, this is the Maxwell's equations. And I wouldn't explain each term. Basically, H is the magnetic field, E is the electric field. To solve these partial differential equations, that we discretize the space. That for each location, you put the electric field and the magnetic field in different location of a cell. You one cell, another cell, whole matrix of cell putting together to form mostly resemble what I look. It might have, it's kind of very rough discretization, as you see. But if each cell becomes smaller and smaller, I will look more and more realistic in your eyes, right? So if we discretize the space that way, and we can approximate these partial differentials in finite difference. For example, if you have an arbitrary quantity, partial derivative of this function with respect to x, it can be approximated by this finite difference. As long as my grid size is small enough, I can make these partial derivatives as close as I want. But in reality, you can't afford a infinitely small partial differentials, right? You need to have a finite size, right? That's the approximation of this method. To put it into 2D, you have this object, you have this discretized space, and you make the light comes in, and for each grid cell, you can calculate how light propagate in this discretized numerical world. And most importantly, you want to put a layer of boundary to absorb the outgoing waves. Because I didn't realize that we need a boundary when I first started this. Because I would say just let the wave go out. But in reality, in the light scattering business, you have light coming, interact with the particle, and the wave goes out without coming back, right? But numerically, they do come back if you do not have an absorbing boundary. This layer of called there is a method called perfect matching method. So you match the for each layer, you make sure the light wave does not reflect back numerically, right? So that's very important to make that, to mimic our real physics situation.
Going back one slide, by making the discrete grids, are you assuming that each part of that purple blob in one grid is then spherical, so you can go back to your original assumption? Each one in each grid is non-spherical, so.
Yeah, so the idea is, let me redraw it. So you have grids. So the ballpark is here, but this part, of course, this one cell wouldn't represent this. You probably, your particle look like this way. And this one, it's hard to tell whether you feel it or not, but maybe you want to throw it away, and depends on the edges. So So you will see particles not the same as the real particle, but with some edges. So basically, you feel this with, but it's not the same as the real particle. That's another source of error. And we want to make the grid size as smaller, and so it can still represent the true particle.
But there is actually a method, since you're talking about spheres, there is actually a method where you can couple an arbitrary distribution number of spheres, and that's using a T-matrix method. So this is exact for an arbitrary shape, but you can also do things where if you have a whole bunch of spheres in the arbitrary orientation, you can calculate the scattering from them, and that's the sort of thing people do when they're calculating how fractals would scatter.
Okay.
Thank you. Any other questions? Go ahead.
The whole idea behind this to get the particle size distribution in the end?
So this is just solving light scattering by one single particle. And then for size distribution, you need to calculate a whole bunch of different sizes and integrate them afterwards. Is that all questions? I'm not halfway yet, but I'm almost run out of my time. This is an example of how do we use this method to calculate light scattering by this kind of particles. People are interested in this because that's the ice crystal look like in the atmosphere, right? I wouldn't, by the way, there is a feature, there is a large forward scattering peak and relatively smaller in the backward. In the middle, you see smaller, but not exactly in the 90 degree. This is another P12 over P11, which is the 1,2 element versus the 1,1 element, the ratio of it. Just to show you the idea. This is called DDA method. Basically, you can see it's a similar idea of discretizing the space by you have a sphere, for example, you discretize the sphere into small dots. Each small dots, because they are small enough, we can predict it. Just like a molecule, you can solve it. If it's small enough, you know how it behaves. So basically, light comes in scattered by each one of the little dipoles, little dots. And each little dots radiate waves and being seen by all other dipoles, right? So each dipole, you know how does it scatter, and each dipole scatter waves being scattered by all others. In the end, you have a whole system of linear equations, linear algebra manipulation to get it right. But the discretization part is similar to FDTD. FDTD is you can put cubics put it together. This one you have a little bit more flexibility, but still it's the idea of discretization, right? FDTD, I put a link here. Two main code. One is called, this is DD-SCAT, which is the most original idea. It's brought by this version, the author, group of authors from this. Another one called ADDA, Amsterdam DDA method, right? Both works really, really good. So if you want to try, you can go there. If you dare to solve the most exotic particles like this one, you can try it out. I made it work by building this model to represent that, right? And put them together to have a spherical Koch-Lesser fall. But this is too perfect, right, compared to this. So I smashed them a little bit in one dimension to make it more resemble of this, right? This is the work using DDA, actually ADDA, Amsterdam DDA method to solve it, right? I wouldn't show you the example. Now it's T-matrix method, like Brian just mentioned. The T-matrix method, the idea is similar to light scattering by spherical particles. It's just you need to expand your waves into the functional basis you are using. And there are expansion coefficients which are unknown, being solved by the matching condition or boundary condition at the edge. So it is flexible, but there is a catch. If your particle becomes so weird, then the time you spend to match the condition becomes so complicated and even not solvable. So there is a catch. Only so far, people use T-matrix to solve light scattering by ellipsoid or spheroid, which are not, the aspect ratio is not huge. So reasonably middle range aspect ratio, and the refractive index has to be reasonable as well. So that there is a catch there. By the way, the T-matrix, again, maintained by Mashinko. So go check it out and see what's in there now.
Another question then on that. So there must be major trades between computational performance and accuracy here. Is that right?
Yeah.
I'm just thinking of your DDA, how many little tiny dipoles must have been used. So is these quick codes, slow codes?
DDA, it's very efficient if you just want one orientation of the particle. For example, this thing is different this way and this way, right? If you put a different orientation compared to the same orientation, it's different. So if you only want one orientation, DDA give you a very quick solution. But if you want a random orientation, and that takes huge amount of time to do. But T-matrix give you the random orientation for free. Just one simulation give you all that for free. But the T-matrix right now lacks the flexibility of arbitrarily shaped particle. T-matrix right now only does the spheroid, ellipsoid, those kind of regular shaped particles. But yeah, there is always a trade between accuracy and efficiency. Any other questions? Go ahead, please.
Are there any considerations for the medium in which the scattering particles, so let's say within the atmosphere and within water?
Yeah, that's a great question because in ocean and in particle, the differences are the relative refractive index. In ocean, you have much smaller relative refractive index compared to the medium, which we call soft particles, optically soft particles. In that case, DDA would give you very quick, fast solutions. But in atmosphere, the refractive index compared to air for the particle is normally 1.5 or 1.49, something like that. In that case, DDA would not be as efficient as T-matrix or FDTD, something like that. Right? So yeah, the relative refractive index is a huge factor when we decide what to choose when we solve light scattering. Okay. Summary of this, I put the references here. You can look into different methods for this. Some of the methods I did not have chance to touch is geometric optics. It's a ray tracing method. So we mainly use that to solve light scattering by gigantic particles, like ice crystal particles or different particles in the air. We can use geometric because the size is so large compared to the wavelength. It's, in a way, it can be approximated by geometric optics. Okay, now the size distribution. The particle appear in different sizes. They have distribution. These are the size distributions that we commonly use. I want to give you hands up on the log normal distribution. This is often used in the aerosol community, right? Aerosol community use a biomodal log normal. Namely, this is just one mode. You probably have another mode or even triple mode. You have to do the proper size distribution integration there. So the gamma distribution, it's used very often in the cloud community, describing the cloud particle size distribution. And power law, it's used in the ocean community pretty frequently. And to describe the effect of size distribution, we call this the effective radius of the size distribution. If you just think in a native way, you would just use n times r to the integration. But actually, you need to multiply by pi r squared. Namely, it's a size weighted by the area. Weighted by the area. So if you look at it, this G here is average projected area. You cancel out the dimension there. So in the end, you have a dimension of size. By the way, the size distribution NR here shows you the probability of the particle size happens between R and R plus dr. So where's my marker? Oh, right here. This whole thing, NR, dr, it's a probability of this particle size happened between R and R plus dr. Right, that's the idea. So that we can use to calculate these parameters to describe the size distribution. Particularly, the phase function would be for each size, you have a phase matrix times the probability dr, and weighted by the cross section. Weighted by the cross section. That's our weighted phase matrix, and that's the scattering and the cross section. The average cross sections. And a few examples for this gamma distribution. Different A give you different effective radii, right? And different B give you different weights of the distribution, different weights, so that you can calculate the weighted scattering efficiency. For different B, you see the oscillation becomes different. So if you have this the size integration, before I show the mono-sized particle scattering pattern, you have this wild oscillation. But once you integrate over a size distribution, all the oscillatory behavior disappeared. You have much better behaved curve in terms of scattering patterns, right? We can actually, let me try to finish this part. I don't have time to do the radiative transfer part. I'm sorry. This is so.
The afternoon is yours and Brian's, wherever you go.
I think you should do the RTE.
Okay, let me skip this part because we are going to do a polarimetric retrieval of cloud later on. So let's skip this one. So how much time do you give me?
Yeah, I think it would be good just to get through all the RTE, because then I'm going to refer to some of the things that you're presenting when I'm talking about remote sensing.
Yeah, it's just I'm underestimate my. Okay, you know why?
We can also make time in the morning for specs one if we need it, or whatever you want.
Definitely, the hard two piece is short.
Okay. So I can get through the specs one thing pretty quickly. I think it's important to have the basics of RTE because then other talks are going to be talking about things like atmospheric correction and remote sensing. So
Should be
to have
based
those
on this,
basics
right?
that presented, I think that would be really, really nice.
So my thought on why preparing this is I'll give you an overview of the big pictures, right? So the sum of rule is that 1 slide a minute. Apparently for this type of thing, it's not. It's not 1 slide per minute. By the way, that's a lesson my PhD advisor told me. When you go to a professional conference, when you prepare a talk, 1 minute per slide. Do not overdo. If you pack too much in, and people won't follow you. But I got 60 slides, and I got. Well, okay. Let me try to finish within another 30 minutes. So the radiative transfer, it's a way we use to describe light scattering by a group of particles. Like light scattering, it's an interaction of light with a single particle. But that's never the case in nature. In nature, we have atmosphere. The molecules are so packed and keep constantly colliding to each other, right? If you have a volume here, guess how many particles in there? There are a huge number of them, right? So that's never the light scattering cannot give us the light distribution, right? We use the radiative transfer theory to do that. That's a theory to describe light coming, scattered by here to here, and scattered again, bounce around, and you can see how difficult it is, right? That's what we call. But before we do that, we introduce some basic terminologies, like this is I, we call readings. Readings is defined in this way. You have a small element area, light goes through it, it's confined in a solid angle dq. This dq forms an angle to the norm by theta. So the readings is a ratio of the total energy per projected area. D sigma times cosine theta is a projected area. Project this area into the direction of this d omega. Per solid angle, per wavelength, per unit time. That's the definition of readings. And flux would be the readings times cosine theta. Basically, you cancel out this term here and do integration over the solid angle. So you basically, it's the total energy. No, not energy. This is a power because energy per dt is a power. Power per unit wavelength. This is called E readings. E readings. Some textbooks use E readings and flux interchangeably, which is not completely appropriate because flux, we have another dimension here is lambda. If you integrate these E readings with the lambda wavelength, then you get flux, right? So if you say people use a flux to refer to E readings, this is a very old practice. We don't use that anymore. Or maybe I'm not completely right. But I think the norm is use E readings for this quantity, and you integrate lambda, you get flux. And again, you can see the terminology now, IQ, UV. It's the same as I introduced in the light scattering section. Stokes parameters appear again. So yeah, again, yes, we in the radiative transfer, we still use the Stokes parameters to describe the polarization nature of light. Even though this is a operational definition, I put it this way. Operational definition is just you measure the total energy without considering how it's coming from, but it's consistent with the light scattering theory. And the reason for this different definition is that the radiative transfer theory has been developing phenomenologically. It's a different island from the main physics theme, right? So then the connection between Maxwell's equations and radiative transfer theories takes people a long time to get it. One of the pioneers it's Michael Mishenko. I mentioned earlier in the light scattering theory that he's the one who did a lot of work on that, connecting the physics Maxwell's equations to the radiative transfer theory we are talking about right now to make it one field. The interaction between a beam of light with turbulent matter, mainly we talk about, it's by particles, scattering and absorption by particles, including molecules, aerosols, clouds, and hydrosols, which we can all solve by FDTD, DDA, or Mie theory, the method we talk about. That's why I spend time on those things. It's very much relevant. Reflection by surface, or transmission through the surface, which is ocean surface. Absorption by gas molecule, which is different. So, surface reflection, we use different terms to describe how light is scattered by a surface. This is readings along a direction. This is downvarying E readings. So think, let me quickly go to the next one. So you see a light comes in and is scattered by this surface, right? You have different surface, like this is a Lambertian, this is a kind of glossy surface, this is a mirror reflection. Different surface give you different distribution of light. This is just a way of describing how the reflection light depends on the viewing angles. There are two different terms. I used to use BRDF, bidirectional reflectance distribution function, to call this one. But Brian told me this is not called BRDF, this is called BRF, bidirectional reflectance factor, from the land remote sensing community. Right? So I corrected here, introduced two terms, but no matter how do you call it, it tells you the same information because they only differ by one constant factor, which is pi. And wavelength dependence, it's implicitly assumed for everything. For this Lambertian, you see different, for this incident light, the same light coming in different direction, the reflection intensity is kind of different. The reason is the causing angle. So you have the same light down here or going in this sideways to the ground. The projected area on the surface are different. So per each unit projected area, the intensities are different. So that's why you have this different intensity of reflection light. And for the scattering part, I mostly covered it. I will cover a little bit on the gas absorption. Gas absorption works this way. If you have very hot black body radiation, which is a continuous distribution of light, passing through a cold cloud of gas, and this is prisms to separate the light. It's a spectrometer, so you can see different light spectrum in the light. You started to see these dark lines. This is the emission line, which coincide with this absorption line, right? This tells you what wavelength does that particular gas absorb. The position of this and the strength of how much light is absorbed depends on the microphysical energy structure of the molecule. The energy structures. The energy consists of different levels. For example, the atom level, the electrons jump from lower to higher energy levels. And also the molecule itself has bonds between different atoms. They vibrate or stretch, they rotate, and they rotate this way, different ways. All that thing will impact the location of these energy levels. The energy of light depends on the energy difference between this excited energy level and the ground level energy, right? And the frequency times h give you the energy difference of the transition. So I put a different symbol here: rotation, vibration, electron, and translational. The translational we normally does not, it's a very small part of it. And this level is very high energy that you can start to see. Then rotation and vibration will affect us the most. The spectral is the spectrum of the absorption lines. But each transition is not monochromatic due to different broadening mechanisms. So the natural broadening is just that for a molecule or atom at a certain energy level, it cannot stay there forever. It has certain lifetime. After a while, it will jump into a lower state, right? That because the finite lifetime, it gives you a natural broadening. I probably don't want to go into this too much detail. My time is again runs out. Sorry, I skipped this one. And another pressure broadening is that the collision between different atoms. So if you have atom by itself, only natural broadening will happen in that case. But of course, if it has speed or velocities, it will be impacted by another broadening mechanism. But if you have many molecules, they collide into each other. If they collide, they will perturb the energy state. So that causes the broadening mechanism. The Doppler, if you have a velocity along a different direction, the frequency will be impacted by Doppler broadening. Namely, if you have a stationary source, it emits light in this way, but if it's moving in this direction, you see the wavefront are compressed. Correspondingly, the frequency is higher. In the back, the wavefront is separating further. The frequency is lower. So in that way, you see different frequency depends on the direction. And for the velocity of the molecules, they have a distribution. They go in this way, that way, up and down, and with different magnitude. And then you can imagine the broadening due to that motion is also a Gaussian type. But putting everything together, we have these main mechanisms: Doppler broadening, collision broadening, and also natural broadening. It's quite narrow. So we put everything together. It's more, if I avoid it, this is a term we use to describe how they broad, not just one single frequency. They have a absorption profile in the frequency domain. I feel that this is kind of complicated now, but so in the way, for each line, absorption line, it has a distribution. This is different line, different line. And if you measure at a frequency, it's a measurement of so many absorption lines from so many different molecules. There is a huge amount of absorption lines. We have a database called HighChain. Scientists use very high accuracy measurement trying to characterize these different absorption lines. And you think you are measuring only one single frequency absorption, but that has contribution of so many other lines. And that's what you see there. That's what you see, this curve in different molecules. They absorb differently, but each, if you draw a very single line here, single line has contribution of so many nearby lines. If you want to resolve that line, you need to make the spectral frequency very, very fine to resolve it. Brian explained this morning on this nature. This I list the notable absorption lines of different molecules. Particularly, you can see carbon dioxide. You have in these wavelengths. I'm more familiar with the wavelengths. I'm not familiar with the 1/cm. That's the wave number that other community might use that more. I use the wavelength, which is micron. For this, you have this 1.6 and 2 micron. These are the wavelengths that OCO2 mission are using that to detect how much carbon dioxide is in the atmosphere. Oxygen, you see this 0.76 and 0.69. This is called oxygen B band. This is called oxygen A band. And water vapor, you can see these different bands. The famous 1.38 band, it's broadly used in satellite remote sensing. This is, again, the same picture, but I want to emphasize that in this region, spectral region, particularly smaller than 4 micron, it's more dominated by solar light. If you do measurement on Earth, around 4 micron is dominated by the solar radiation, and longer than that is dominated by the Earth's radiation itself, thermal radiation. This is a behavior of black body radiation, depends on the temperature solely. I spend most of my time developing radiative transfer models in the visible, namely like the short wavelength side. And in the infrared or microwave community, they started to talk to me, can your code handle the long wave infrared or microwave region? Not yet. It's different. The source is different, and the nature of source is different, so you have to handle it differently. Finally, radiative transfer. Let's start with the Beer law. Beer law is just the absorption of light. This is readings, by the way. Absorption of light is proportional to the light, the intensity itself. You absorb something, if you, how do I have an analogy? Okay, if you have 2 kids in the room running around, the chance of them bumping into each other is much smaller than 10 kids in the same room running randomly, right? That's the idea. The absorption of readings is proportional to the readings magnitude itself. And mathematically, that lead to the Lambertian law. And a few terminology, we call this absorption coefficient. The dimension is 1/meter, which is the absorption cross-section that we talked about, times the number density of the particles. The number density is number per cubic meter times the area give you inverse meter. So I want to spend time on this, because physicists mostly use a dimension analysis to figure out many things. One of the examples is the Rayleigh scattering. You can just use a dimension analysis to get the 1/lambda power of 4. This ds is the path increment. You times this together, do an integral, give you a dimensionless quantity called optical depth. It's a depth, but optical depth. There is keyword there, optical depth. It describes how efficient that a medium optically interact with light. So this is a Lambertian law of light passing a incremental distance of s. That's how a decrease got extincted or absorbed. And if this is a constant in this domain, then you can just write it as beta A times S, and that's how we calculate the transmitted radiations through a medium. And this quantity is defined as transmittance exponential minus tau. It's just the ratio of transmitted light compared to the incident light. Okay, that's just the absorption. If scattering is present, then you can see the light will start to show up in other directions, not just your incident directions. And in that case, the differential of the readings is proportional to the extinction times I, which is the same as the Lambertian law we just covered, plus a source term due to scattering. The scattering is described by this called phase function. If it's polarized light, it's phase matrix. It's incident light times, this is incident light, times the phase matrix or phase function give you the light distribution of scattered after the interaction. And note that we have this scattering albedo, which is the ratio of scattered light to the total light which is removed from the incident light. It's a single scattering albedo. Single scattering albedo, it's 1, so no absorption in that case. If single scattering albedo is 0, no scattering in that interaction, right? Two extreme cases. And in the end, we need to solve this equation. So sorry for the math that if you saw this before, you know. If you did not solve this, did not see this before, apparently you cannot get it in a few minutes. But just show you, we are trying to solve this equation by doing all kinds of mathematical modeling, right? That's what I do mostly. And again, this is optical depth. It's addition of absorption and scattering coefficients. And remember the dimension of this is 1 over meter. This is meter. In the end, you have a dimensionless quantity, right? And let me try to finish this soon. So mostly we deal with a plane parallel configuration because the Earth is a spherical environment, right? So it's harder to do that. So we approximate the Earth's atmosphere as a flat medium because the Earth's radius is very large. And in that geometry, as long as we do not look sideways too much, if we just look down, the Earth behaves pretty much a plane parallel medium. In that case, we can solve it relatively easier. Again, I fast forward on this different category. I cover some of that. So in the solar spectrum region, it's mostly less than 4 micron. And the emission of atmosphere is not important purely because of the temperature of the atmosphere. And we have to deal with absorption and scattering. In thermal infrared region, it's longer than 4 micron. Then you just need to take care of the Earth's thermal emission. These slides, I mainly want to see a convention that the radiative transfer community use. One way to define is that you set your zeros here and z got increased this way. Another way is to set your zero to be at the top of the atmosphere and increase down. So in this way, Sorry, I might not, do this more carefully. Let me. So different from the previous slides, this convention, we define this as a zero of optical depth. Namely, at TOA, tau is 0. At the bottom of TOA, it's a maximum of the atmosphere. Of course, you get into the ocean, you have additional optical depths. And this Z and the tau increase in different direction. That's another convention. Consequently, the radiative transform from here to here, the difference is this minus sign here. Minus, minus, plus, minus, and this minus becomes, plus becomes minus. This is purely a convention thing, geometric definition thing. So sometimes you see this, sometimes you see that. Don't be tricked. It's just the same thing, right? When we're dealing with polarization, we need to remember that when we define the Stokes parameters, we have to use a plane of reference, a reference plane. But when you have multiple scatterings bounce around, what is your reference plane? For a single scattering, it's just a scattering plane, right? The plane which contains the incident light and the scattered light. But in multiple scattering, we trace the reference plane carefully. So this is incident light. The reference plane is determined by the z-axis and this direction of propagation. That's the reference plane. And upon scattering, and the scattered light reference plane is defined again, this direction and the vertical zenith. And the scattering plane is here. So first you rotate your reference plane from this meridian plane to the scattering plane, and after the scattering you rotate it back to the meridian plane. So the most prevailing use of reference plane, it's the meridian plane. So whatever direction you are talking about, and the vertical up direction, that's your reference plane. This is critical when we interpret the Q and U. So for pacemaker, you have this polarimetric measurement, IQU. Remember, Q and U are referenced in terms of the local meridian plane. And for different plane, the numbers are different. That's the message I try to deliver. And that's just mathematically how do we convert between difference. I skip this one. This is just one of the methods we use to solve the RT equation, which is my what I have been working on for a long time. Let me just skip this one. I probably just stop here. Yeah. Sorry that I couldn't finish in 1 hour. It's apparently too much. Apparently too much, yeah.